Welcome to my channel. In today's class, we look at three major subtopics in linear algebra. First, I'll be looking at how to find determinant of higher order matrices. And in determining the determinant of higher order matrices, I'll show you three ways of doing that. That two ways in the first video, and then one way which is elementary row operations in the second video. And then after that, we look at how to find the inverse of the matrix, higher order matrices. And again, I'll show you two ways of doing this. And then in the last video, I'll be showing you how to solve systems of elementary row systems of linear equations by use of inverses. I'm aware that in the other videos we did how to solve systems of linear equations by use of Gaussian elimination and Gauss-Jordan elimination. So in today's video, we'll look at another method of solving systems of linear equations, and that will be by use of inverses. So join me to the end of this video, and if you're not subscribed, remember to subscribe so that you can be getting the videos whenever I upload. Thank you. Welcome to my channel, and let's look at how to find determinant of higher order matrices. So we begin with finding determinant of a 3 by 3 matrix, and then we generalize this knowledge to higher order square matrices. So for example, I look at how to find determinant of 4 by 4 matrix, and then you understand that it's just the same way. So we just generalize the knowledge that we'll have acquired in 3 by 3 matrix. So look at an example. Let A be this matrix. Find det A. That means find the determinant of A. Now, so I found the determinant here. These two vertical lines I'll use them as a command to find determinants. So these two vertical lines means find determinant. So you can see I've used them. It means find the determinant of this 3 by 3 matrix. So the formula is that I'll take this element here, this element 1, and multiply it by a matrix of the determinant, multiplied by the determinant of a matrix that remains when I delete the row that 1 is in, that is row 1, and delete the column of 1. So when I delete the row of 1 and the column of 1, the matrix that is left is 3, 5, 7, 6. So I've taken this element 1 and multiplied by that the determinant of that matrix that remains on deleting row 1 and deleting row 2. And then the next thing will be minus 2. Minus 2 multiplied by the determinant of the matrix that remains, the determinant of the matrix that remains when I delete the row of 2 and the column of 2. So on deleting the row of 2 and the column of 2, the matrix that is left is 2, 5, 3, 6. 2, 5, 3, 6. So it's minus 2 times the determinant of that matrix. And then plus 3 times the determinant of the matrix that is left when I delete the row of 3 and the column of 3. So when I delete the row of 3 and the column of 3, the matrix that is left is this 2, 3, 3, 7. So this is supposed to be 3, not 1. This is supposed to be 3. Now, so one may ask, where am I getting the signs plus, minus, plus, and so on. So the signs are given by -1 raised to I plus j, where ij is the position of that element. This I is the column of that element, and j is, no, I is the row of that element, and j is the column of that element. For instance, element 1 here, what sign should I use? So element 1 is in row 1, column 1. So the sign that I should use should be -1 raised to 1 plus 1, which is -1 raised to 2, -1 raised to 2, and this would be plus, this should be a positive sign. It should be a positive sign. When I raise -1 to 2, the sign will be positive. What about here? What about here? 2, element 2. What sign should I use? So I should take -1 raised to, this element 2 is in row 1, column 2. And so you notice that this is -1 raised to 3. So the sign will be negative. So that's why I have -2. What about here? Why do I have +3? So I go to where 3 is, and 3 is in row 1, column 3. So the sign will be -1 raised to row 1 plus column 3. So this is -1 raised to an even number, and the sign will be positive. So that's why you can see I have positive there. So what that means again is that these signs will be alternating. So we begin with a positive sign, then go to a negative sign, then a positive sign, then negative sign, positive sign, negative sign, and so on. Even you can go downwards. If this is positive, this will be negative sign, positive sign, negative sign, positive sign, and so on. Now, so in this example, we found the determinant of this matrix along the first row. So we just proceed. This will be 1 multiplied by this determinant minus 2 multiplied by this determinant plus 3 multiplied by this determinant. What is this determinant? This is 18 minus that 5. And that's what I have here. 1 multiplied by 18 minus that 5. Then minus 2. The determinant here is 12 minus 15. 12 minus 15. And this is 14 minus 9. So that's what I have. Using a calculator, you find this determinant to be 4. Now, so what this means again is that we can find the determinant of this matrix along any row and along any column. So look at this. We found it along row 1. You can also decide to find along row 2, or along column 1, or along column 2. So let's try and do it along column 1. Along column 1, you notice that this will be positive, the sign will be positive, the sign will be positive, negative, positive. So what we did is that we take the element 1, this 1, multiplied by the determinant of the matrix that is left when I delete the row of 1 and the column of 1. So when I delete the row of 1 and the column of 1, the matrix that is left is 3, 5, and then 7, 6. Then the next sign is negative, and the element is 2. Negative, and the element is 2. So what happens when I delete the row of 2 and the column of 2? The matrix that is left is 2, 3, 7, 6. Then the next sign, it was positive, negative, positive. The positive 3. What happens when I delete the row of 3 and the column of 3. What matrix do I remain with? So deleting the row of 3 and the column of 3, I'm left with 2, 3 and 3, 5. 3, 5. So this will give us the determinant of that matrix. And remember, I've said that we can find this determinant along any row and along any column. We only need to know the signs. So let's see, this will be 30 minus 35, which is 5. 30 minus 35, which is negative 35, multiplied by this one to be negative 5. If I multiply by this one, I still get negative 5. Then what about this? This will be, there's a negative 2 here, multiplied by, this is 12 minus 21. 12 minus 21. Then plus 3, multiplied by, this is 10 minus 9. 10 minus 9. This was 18. This was 18. Oh, this is not correct here. This is not correct here. This was 18 minus 35. I don't know why I found the negative 5 from. That was not correct. It was not correct. So this was minus 2. So this is 18 minus that 5. That's correct now. And this is 12 minus 21. And this is 10 minus 9. And so what is 18 minus 35? This is negative 17. It's negative 17. What about 12 minus 21? This is negative 9. Negative 9 times negative 2 be plus 18. Plus 18. And this is 1 times 3, which will be 3. So this is 1 plus 3, which is 4. So you can see, we have found it again along the first column. So you can even do it along the second column, and you'll still get the same result. Now, there's another way for a 3 by 3 matrix, another easier way of finding a determinant of a 3 by 3 matrix. And this is the alternative way that I've shown. Now, this alternative way, what I did was, I wrote the matrix that I was given here. This is the matrix that I was given. 1, 2, 3, 2, 3, 5, 3, 7, 6, 8. That's the matrix that I was given. Let me just confirm. Let's confirm. The matrix that we were supposed to find the determinant. Yes, 1, 3, 1, 2, 3, 2, 3, 5, 3, 7, 6. 2, 3, 5, 3, 7, 6. Yes. That's the matrix that we were given. Now, so you take that matrix, you write it here. I've written that matrix here. And then I've taken these 2 columns. These 2 columns, I've added them here. So you add these 2 columns here. And then you notice that there will be 3 columns. These 3 diagonals running from left to right. There will be these 3 diagonals running from left to right. You multiply along these diagonals and add the result. So you can see I've written here plus, plus, plus. So when I multiply this diagonal, I get 18. Then along this diagonal, I get 30. Along this diagonal, I get 42. Then there's these other 3 diagonals running from right to left. These are the 3 diagonals running from right to left. You multiply along these diagonals and subtract the result. So you can see I've written here minus, minus, minus. So when I multiply along this diagonal, this will be 4 times 6, which is 24. So I subtract it, and this will be 35. I subtract it, and this will be 27. I subtract it. So when I do the whole of this, I get 4 as the determinant. So for a 3 by 3 matrix, this method will work. This method will work for 3 by 3 matrix. But the earlier method would work for any other square matrix. It will work for 3 by 3, it will work for 4 by 4, it will work for 5 by 5, and so on. Now, so we have this other example. We want to find the determinant. This is still a 3 by 3 matrix. So I want to use the two methods and see that the two methods work for this matrix and for any other matrix. So we begin with the first method. And I want to find it along the first column. I want to find along the first column. So you remember the sign will be positive, negative, positive. But for this element, you see this is negative here. So this will be negative. This will So you notice that this sign here, just as we had said earlier, these signs are positive, negative, positive. So if this is positive, negative, then this will be positive, and this will be negative, and so on. So if this is positive, then this will be negative, and this will be positive. So that's how the signs go. And we say they just alternate. So that is the knowledge we have. And therefore, want to do it along the first column. So it will be positive, as we've already said, positive, negative, positive. So the limit there is 1. And then the determinant of the matrix, that remains when I delete the row of 1 and the column of 1. That matrix is 2, negative 2, negative 1, 2. And that's the matrix I have. Then let me just add the next one. But you know that anything multiplied by 0 will be 0. So, but let's just put it negative 0. And delete the row of 0 and the column of 0. And what you have left is 2, negative 1, negative 1, 2. That's what I have. And then next is sign is positive. And so positive 1, delete the row of 1 and the column of 1. You have 2, negative 1, 2, negative 2. So that's what I'm left with. Now multiply this. This will be 4. 4 minus 3. No, minus 2. 4 minus 2. And this will be 0. Nothing multiplied by 0 will be 0. So there's no need of multiplying inside here. This will be negative 4 plus 2. So when I do this, I find that this matrix has a determinant of 0. Now let's use the other method and see whether it works. And we said it will work for any 3 by 3 matrix. So for that other method, I want to write the matrix here and add the first 2 columns here. So the first column is this, and the second column is that add. Then identify these 3 diagonals running from left to right, and multiply along these diagonals as we add the results. So this will be 4 minus 4 plus 0. And this other one will be negative 0. I began from here, there's no problem. I began from here. So this will be negative 2. So when I subtract negative 2, I get positive 2. And then this will be positive 2, subtract it, and this will be 0, subtract it. So when I do this, I get 4. No, I get 0 as the determinant of this matrix. And so that is how we find the determinant of matrices of higher order. Welcome back. In the video that just ended, we saw that we can find the determinants of matrices along in a row or along in a column. And so the video that follows, we look at another way of finding determinants of higher order matrices. And in this video, we're looking at how to use elementary row operations to find the determinant. Welcome to my channel, and let's see how to find the determinant of higher order matrices using elementary row operation. So we begin with the 3x3 matrix and then generalize this knowledge to any other higher order square matrix. Now, so we'll be using elementary row operations. In this example, I'll be reducing my matrix to echelon form, then multiply the entries along the diagonal. Those entries along the diagonal will give me the product of those entries along the diagonal. After reducing that matrix to echelon form, will give me the determinant of that matrix. Now let's look at this first example. Find the determinant. Find the determinant of this matrix A. So I've got this vertical line that mean determinant. That is a command to find the determinant. Now, so I want to obtain non-elements below this diagonal. I want the elements below this diagonal to be 0. Elements below this diagonal, I want them to be 0. So what I do, I take this leading element and use it to create those below it to be 0. So how do I get this element to be 0 and this one to be 0? So to get the element in row 2 to be 0, I'll take the current row 2, then minus 2 multiplied by row 1. So this will give me my new row 2. And then I also want this element to be 0. This element is in row 3, so I take row 3 and subtract 3 multiplied by row 1 to give my new row 3. So let's just do that. Row 1 remains where it is. 2 minus 2 multiplied by 1, and that gives me 0. 3 minus 2 multiplied by 2, that gives me negative 1. 5 minus 2 multiplied by this 3, that gives me negative 1. So I'm done with the second row. I go to the third row, and remember the third row, you say that we take the current third row minus 3 multiplied by the row 1 to give me the new row 3. So in other words, 3 minus 3 multiplied by 1, that gives me 0. 7 minus 3 multiplied by 2, this 2, that gives me 1. And then negative 6 minus 3 multiplied by 3, that gives me negative 3. So I have this row. So I'm done with the first column. Done with the first column. I come to the second column. I have this leading entry here. I use this leading entry to create the entries below it to be zeros. So I want to use it to make the entries below it to be 0. I'm not touching the row, the column, the elements above it. I'm only touching the elements below. So you notice that for me to get row 3 to be 0, I will take that row 3 and add row 2. This gives me my new row 3. So first row remains where it is, second row remains where it is, but now second row plus third row, -1 plus 1 gives me 0, and then -1 plus -3 gives me -4. And my matrix in echelon form. So you can see these elements, I've written them to be blue, that you see that the elements along the diagonal that I want. So if I multiply along that diagonal, what I get is the determinant of this matrix. So that's what I did. I took +1 times -1 times -4, and that gives me 4. So 4 is the determinant of this matrix. And this method will apply for any other square matrix. Let's look for at another example. This time I have a 4 by 4 matrix. And the question is, find this. So this means determinant. Find determinant of this matrix. That's what the question says. So I'll do what I did in the first example. I want the elements below this diagonal to be 0. The elements below that diagonal, I want them to be 0. So that's what I want. So to get these ones to be 0, I use this first element. And I want to use this element to make this one 0, this one 0, this one 0. So how do I achieve that? So to make this element here 0, I would have, that element is in row 2. So I would have row 2 minus 2 multiplied by row 1. So this would be 0. Then I want this one also to be 0. This element is in row 3, so I would have row 3 plus row 1. So this gives me the new row 3, and this was to give me new row 2. What about this? This element is in row 4. So I would have row 4 minus 2 row 1. So this will give me the new row 4. So let's just do this and see what we get. So the first row remains where it is. Now, 4 minus 2 multiplied by 2, that is 0. 5 minus 2 multiplied by 1 is 1. That gives me 3. And then -3 minus 2 multiplied by -1. And this gives me, this will be +2 here. Subtract +2 here, added to -3, gives me -1. And then finally you have this 6 minus 2 multiplied by this 2. And that is what gives me this 2. I'm done with the first row. I got the second row, the third row. I'm done with the second row. I got the third row. And remember that the third row, I want to get it by just adding the current third row plus row 1. So 2 plus -2 is 0. 1 plus 5 is 6. -1 plus -2 is -3. And then 2 plus 6 is 8. So I'm done with that. I go to the last row. So going to the last row, I said that I take row 4 minus 2 multiplied by row 1. So 4 minus 2 multiplied by 2 is 0. 11 minus 2 multiplied by 1 is 9. -4 minus 2 multiplied by -2, multiplied by -1 this negative 1. This will be negative 2. And then 8 minus 2 multiplied by 2. This will be 4. So I'm done with this, the first column. I'm done with the first column. I come to the second column and I notice that my leading element is here. That's my leading element. So I use this element to create zeros below it. So I need a 0 here and another 0 here. So how do I achieve a 0 in this position? So this element is in row 3. So I'll take row 3 minus 2 multiplied by row 2. That will give me the current, the new row 3. Then this element, I need a 0 here. And this element is in row 4. So I'll take row 4 minus 3 multiplied by row 2. And that will give me the new row 4. That's what I want to do. So you can see that I have this row here and this second row, they remain the way they are. So I only want to change third and fourth row because these are the rows that I want zeros to be. I want zeros here in those 2 rows. So what do I get here? Row 3, the element there is 6 minus 2 row 2. The element in row 2 is 3, and that gives me this 0. And then negative 3 minus 2 multiplied by negative 1, that gives me negative 1. And then 8 minus 2 multiplied by 2, that gives me this 4. Then now I come to this other row. Remember that it's minus 3 row 2. So 9 minus 3, the element in row 2 is 3, and that will give me 0. And then I have negative 2 here, minus 3, the element in row 2 is negative 1. Negative 1, this will be positive 3 here. So the result is positive 1. And then 4 minus 3, the element in row 2 is 2. And this will be negative 2. So I'm done with the second column. I'm done with the second column. I come to the third column and I notice that this is the leading element. So I think of using this element, how do I get a 0 here? So I notice that I only need to add row 3 plus row 4. And this will give me the new row 4. That will give me the new row 4. So that's what I did. So the first, second, and third rows remain the way they are. So let me just move this one a bit and move it up. So as I said, the first, second, and third rows remain the way they are. Then I just need now to add row 3 to row 4 to get the new row 4. So this negative 1 plus 1 will give me 0. And this positive 4 plus negative 2 gives me 2. I've acquired what I wanted, because what I wanted was that the elements under this diagonal be 0. The elements under this diagonal be 0, and that's what I have. So once I achieve that, then I just multiply these entries along this diagonal to get the determinant of the matrix. So I said multiplying the blue elements along the leading diagonal, we obtain 2 times 3 times negative 1 times 2, and that is negative 12. So negative 12 is the determinant of this matrix. So, and that is how we get the determinant of higher order matrices by row reduction. Now, so those are the ways of finding determinants of higher order matrices. Let's now focus on how to find the inverse of higher order matrices, and we begin by the method of adjoint. So how do you find an inverse of higher order matrix by method of adjoint? Welcome to my channel, and let's look at how to find inverses of higher order matrices using the method of adjoint. Now, we already know how to find the determinant of matrix, and that is very important in this topic. So the following steps are used for us to get the determinant of higher order matrices. No, the inverse of higher order matrices. So the first thing that we do to get the inverse of higher order matrices is to find the inverse of the matrix. So supposing I'm given matrix A, then the first thing I will do is to find the determinant of matrix A. Then I will proceed to find the cofactor matrix of matrix A, and then find the adjoint of matrix A. So for higher order matrices, the adjoint of matrix would be the transpose of the cofactor matrix that we obtained in part 2 here. So this part 2 is not this. It's part 2. So the transpose of this matrix in part 2 is the adjoint of that matrix. So once we have this adjoint, and you remember that the inverse of matrix A is 1 over determinant times the adjoint of matrix A. Let me remind you how to find the adjoint of a 2 by 2 matrix. So if I have a 2 by 2 matrix, A, B, C, D, if this is a 2 by 2 matrix. So what is the adjoint of this matrix? So the adjoint of this 2 by 2 matrix, I'll abbreviate it as adjoint. So the adjoint of this matrix, supposing this is matrix A, so the adjoint of this matrix A is the matrix that you get when you interchange this D, A, and then interchange the signs. Now, if the sign is positive, then it must be negative this time. And this is also positive, so we have negative. So you just change the sign. So if the sign was positive, it becomes negative. And if it was negative, it becomes positive. This is the adjoint of this matrix. For a 2 by 2 matrix, that's what we do. Now, so what is now important for us is how do we get the adjoint of a 3 by 3 matrix, a 4 by 4 matrix, and a 5 by 5 matrix, and so on. And that's what I've written in. That the adjoint of matrix A of higher order will be the same as the transpose of the cofactor matrix that we obtained in the transpose. So again, let me just remind you what the transpose is. And the transpose of a matrix is the new matrix that you obtain when you make the rows become columns, or when you make columns become rows. So for example, if this is the matrix A, B, C, D, E, F. So the adjoint of A, now the transpose of A, which we denote as A transpose, will be the matrix you obtain when you make the first row be the first column, the second row be the second column, and so on. So this is the transpose of this matrix. Now, so what now remains is for us to learn how to get the cofactor matrix. Once we know how to get the cofactor matrix, we shall get the transpose of that cofactor matrix, and that will give us the adjoint of matrix. And then once we have this adjoint and we have the determinant of the matrix, it's now easier for us to get the inverse of that matrix. So let's look at an example. So this is my example, and the question says, using adjoint method, find A inverse if A is this. Using adjoint method, find A inverse if A is this. So the first thing we do is to find the determinant of A. And since A is a 3 by 3 matrix, I chose on the simplest way to find the determinant of A. And so I write, as we looked at the previous, as we did in the previous video of finding the determinant of matrices, I wrote matrix A here, and then took these first two columns and added them here. The first two columns, added them here. So I have these diagonals, 3 diagonals, running from left to right. These 3 diagonals, I multiply along this diagonal and add. You can see this is plus. So I add, this is -5 plus, this is -6 plus, and this is -8. And then minus these entries, minus, this is -10, and this is -6, and this is -4. So when I do this, I get the determinant to be 1. So I now have the determinant. What I want to look for is the cofactor matrix. And then, after getting the cofactor matrix, I'll find its transpose, and that will give me the adjoint. So the cofactor matrix, let's just remember what our matrix was. Let me write what the matrix was. No, the matrix, I can just get it from here. It was 1, 2, -4, -1, -1, 3, -1, -2, 5. So that is the matrix. Now, so to get the cofactor, I get the cofactor for every element. I get the cofactor for every element. So for example, this element here, its cofactor will be the determinant of the matrix that remains when I delete the row of that element and the column of that element. So when I delete the row of 1 and the column of 1, the matrix that is left is this: -1, 3, -2, 5, -1, 3, -2, 5. And then I come to the second element is 2. I get its cofactor. So I delete the row of 2 and the column of 2. The matrix that is left is -1, 3, -1, 5. So -1, 3, -1, 5. So you may be asking, what about this sign? And this sign we already discussed in the determinant when we were looking at the determinants of matrices, and we said that if our matrix, you see this is our matrix, 1, 2, -4, -1, -3, no, this is -1, 3, and this is -1, -2, 5. So we said that the sign for this element will be positive, this will be negative, this 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 will be positive, and they alternate. And that's why you can see I put a positive here, and I put a negative here, a positive, negative, positive, negative, positive, negative, positive. So they alternate. Okay, so that's how we find those signs. So we were done with this element and this element. So we come to this other element, and we want, and remember, this is not part of the matrix. It's not part of the matrix. So our matrix was this. This was our matrix. This one we just used it to get the determinants. Now, so we want the cofactor for this element, for this position here. And so this position is in row 1, column 3. So when I delete row 1, column 3, I'm left with this. I'm left with this. -1, -1, -1, -2. And that's what you see. It's a plus. Now I come to this element, delete its row, and delete its column. So I'm left with 2, -4, -2, 5. 2, -4, -2, 5. And the sign is negative. Remember that the signs are alternating. So now let's come to this other element here, the element in row 2, column 2. And remember that this is not part of the matrix. So our matrix remains to be this. So we are on this element. So we delete the row of that element and then the column of that element. We're left with 1, -4, -1, 5. 1, -4, -1, 5. And the sign is positive. Then the next element is this. Delete its row and its column. The matrix that is left is 1, 2, -1, -2. 1, 2, -1, -2, and the sign is positive. Remember, the signs were alternating. And so let's now go to the last row. This element, the column, and not the row, and then the column deleted. We are left with the 2, -4, -1, 3. 2, -4, -1, 3. Then the next element is this. Delete its column and then its row. We are left with 1, -4, -1, 3. 1, -4, -1, 3, and the sign is negative. And then lastly, this element, delete its row and then its column. We have 1, 2, -1, -1. 1, 2, -1, -1. So we've now done that. We only need, what remains is now just to find the determinants. So let's just now find the determinants. And so when we do that, this is what we get. This will be -5, -5, and -6. This gives us +1. Now what about this? This will be -5. There's a minus outside, but inside we have -5 -3. So this becomes positive. So this is -2 times negative, which is +2. What about this? This will be 2 -1. The sign here is positive, so it's 1. So we do that for all the elements, and this is the cofactor matrix. That becomes the cofactor matrix. So remember, we said once you have this cofactor matrix, you get its transpose. You get its transpose. And so what is the transpose of that? We say we shall make the rows become columns, and or make the columns become the rows. So when we make this first row be the first column, yeah, the transpose is that. So first row be the first column, second row be the second column, and the third row be the third column. So this is the adjoint of our matrix. This is the adjoint. Now, so what is the inverse? The inverse of A is 1 over the determinant times the adjoint. So remember our determinant was 1. So times the adjoint. So we just remember the same adjoint is the inverse. So this is the inverse of matrix A. Let's look at another example to make our working clear. So here is the question. And the question says, use adjoint method to find the inverse of this matrix. Remember, this power means inverse. Power -1 means inverse. So again, I've chosen on the method that I said will be easier for a 3x3 matrix to find the determinant. So we find the determinant, we have this matrix, we write it here, and then add the first two columns here, and multiply along this diagonal and add, along this diagonal and add, this other diagonal and add. And then subtract the product along this diagonal, subtract the product along this diagonal, and subtract the product along this other diagonal. When that happens, we find our determinant as -26. From there, what the next thing is for us to get the cofactor matrix. So what was our matrix? Let's just write what our matrix was. Our matrix was 2, 1, -2. Just a minute. I want to create a space to write that matrix. It was 2, 1. Let me just write it on a piece of paper and then I get a place to write. So the matrix that we were given was 2, 1, -2, 3, -3, -1, and then 1, -2, 3. So let me just write it somewhere now so that we use it to find the cofactor matrix. Good. Let me now write it. Let me just write the matrix that as we refer to it, it becomes easy. So the matrix is 2, 1, -2, and 3, -3, -1, and then 1, -2, 3. This is the matrix. So we want to get the cofactor matrix. We got this, we go for this first element here. And remember the sign will be positive, negative, positive, negative, positive, negative, positive, negative, positive. So that is how the signs will alternate, and that's, we already talked about that. So to get the cofactor in this position, delete first row, delete first column. We are left with this matrix: -3, -1, -2, 3. Find its determinant. And then the sign, next sign is negative. Now we are in this position. Delete the row and the column. In this position, delete the row and the column. We are left with the 3, 1, -1, 3. 3, 1, -1, 3. The next sign is positive. We are here. The next sign is positive. Delete this row and that column. This row and that column. So you are left with the 3, -3, 1, -2. 3, -3, 1, -2. Then finally, next, this was positive, negative, positive. This will be negative. So in this position, delete this row and delete that column. So level 1, -2, -2. So we do that for all the other elements. We do that for all the other elements, and then you find the determinant. Find the determinants, and this is the matrix you end up with. This is the cofactor matrix. This is the cofactor matrix. Now, so we find its the adjoint by finding the transpose of this matrix. So this is the matrix we have. So let's find the transpose. Make this first row to be the first column. This second row be the second column. This third row be the third column. So this is the adjoint matrix. So our question was to find the inverse. And the inverse is 1 over determinant times the adjoint. And this is our determinant, negative 26. So 1 over negative 26 times the adjoint. And if you want, you can leave your answer at this point, or you can take these values inside. So when you multiply inside, this becomes positive 11 over 26. This is negative 1 over 26. This is positive 7 over 26, and so on. So this is the inverse of this matrix. And this is how we find the inverse of matrices by use of adjoint. The next video focuses on how to find the inverse of matrix, and in this video we use a method of row reduction. In the earlier one we looked at how to use a method of adjoint. So let's see now how to use row reduction to find the inverse of the same matrices. Welcome to my channel, and today I'll teach you how to find the inverse of higher order matrices using row reduction, or I can say using Gauss-Jordan method. So that's the method I will use today. In the last video we looked at how to get inverse of higher order matrices by using the method of adjoint. So to use this row reduction method, what we must understand is that we'll be carrying out row elementary operations. And what this method says is that supposing I was to write A and then with the inverse, now A with the identity matrix. If I was to write A with the identity matrix, then there will exist elementary row operations that will take A to the identity matrix and then take the identity matrix to the inverse of A. That's what we'll be doing. So we'll be carrying out elementary row operations and ensure that we make this matrix A to become the identity matrix. And those same elementary row operations are performed to the identity matrix, and they carry it to the inverse of A. So let's use an example to make it clear. The question is, use row reduction to find the inverse of A when A is this. So we're using row reduction. So what we do, we write the matrix that we've been asked here, and then there's this vertical line, write the identity matrix. This is a 3 by 3 matrix, and therefore we'll write here the identity matrix, a 3 by 3 identity matrix. So we carry out operations, elementary operations on this to transform it to become the identity matrix. So the elementary row operations that we'll be doing on this matrix, we'll be doing them also on this matrix. So when this one becomes identity matrix, this will have become the inverse of A. So let's just do that. So I have this element here, this element 1. I want to use it to have zeros elsewhere in the column, so that this 1 is the only non-zero element in column 1. So I want a 0 here, another 0 here. So what you notice is that to get the new row 2, I'll have to take the current row 2, then add row 1 to it. Let's do that. So row 1 remains where it is. So add row 1 to row 2, you have a 0 here. Add row 1 to row 2, this 2 plus negative 1, you have negative 1. This negative 4 times, plus 3, you have another negative. What was this? This gave us 1. When you add this 2, and when you add this 2, you have negative 1. When you add these two, you have 1 here. And when you add this and that, you have 1. When you add this and that, you have a 0. So we also require 0 in this third row position, third row column 1 position, this third row column 1 position. So to get a 0 here again, you notice that we shall have to add row 1 plus row 3. That's what I wrote, row 1 plus row 3. So 1 plus negative 1 is 0, 2 plus negative 2 is 0, and then negative 4 plus 5 is 1. 1 plus 0 is 1, 0 plus 0 is 0, 0 plus 1 is 1. So I have this. Now, so the next thing, I'm done with the first column. So I count the second column, and I have this, in this second row, second column of this element. I want this element 1 to be the only non-zero element in column 2. I want it to be the only non-zero element in column 2. So I need this to be 0. This one is already 0. So we are very much fortunate here. This one must be 0. So for us to have this become 0, what are we to do? We're supposed to take row 1 minus 2 row 2, and this should be our new row 2. So row 1 minus 2 row 2. So that means 1 minus 2 times this will remain to be 1. 2 minus 2 times this will be 0. That's the 0 you are seeing there. And then negative 4 minus 2 times negative 1. This will be negative 2. And then we come to this 1 minus 2 times 1. And that should be negative 1. That should be negative 1, you see there. And then 0 minus 2 times 1. That should be negative 2. Then finally 0 minus 2 times that will be 0. So you have this matrix. So you have this matrix, and you can see we've achieved that we have a 1, then zeros below it. Then we have this 1, then zeros above and below. So we now come to this element and use it to create zeros elsewhere, so that it's the only non-zero element in this column. So what are we to do? And I've written here that for us to achieve that, we shall require row 2. The new row 2 will be row 3 plus row 2. What about here? To get a 0 here. To get a 0 here, we require this row 1 plus 2 row 3. This element plus 2 times this gives us a 0 there. So that's what I did. So this row remains what it is. This row remains what it is. We only want to affect row 2 and row 1. So let's begin with row 2. To get a 0 in this position, we say we are adding row 3 plus row 2. So this 1 plus this negative 1 gives us 0. This 1 plus this 1 gives us 2. This 0 plus this 1 gives us 1. And this 1 plus this 0 gives us 1. So we are done with this row. So you come to this other row. Remember that we are taking, remember that for us to get a 0 in this position, we are taking this element times 2, then add to this. So this times 2, you get 2, plus this, you have the 0. This times 2, you have 2, plus this, you get 1. This times 2, you have 0, plus this, you have negative 2. This times 2, you have 2, plus this, you get 2. So we've achieved what we wanted, because you notice that the first matrix here has become identity matrix. It has become identity matrix. And so we said, once this becomes the identity matrix, whatever shall be here will be the inverse of matrix A. So in other words, the inverse of matrix A is this matrix 1, negative 2, 2, 2, 1, 1, 1, 0, 1. This is the inverse. The method that will be used is row reduction or Gauss-Jordan. So let's look at another example, just one, to make it clear. And this is the example. Use Gauss-Jordan method to find this inverse. So again, we're just doing the same thing we've been doing. We have this matrix, and then beside it, we write the identity matrix. Do elementary operations on the entire matrix. When this becomes identity, whatever will be here will be the inverse. So remember that for us to make this an identity matrix, we require this element to be 1. So that's the first thing I do. I make it 1. There are various ways of making it 1. We may want to subtract this row 3 from row 1, and this will be 1, will become 1. Or just simply do what I did. I divided row 1 by 2. I divided row 1 by 2. So when you divide row 1 by 2, this one becomes 1, a half, negative 1, a half, 0, 0. So this is the matrix we then get. We use this one that we created to have zeros elsewhere in column 1. So you need a 0 here and a 0 here. So how do we achieve a 0 in row 2? I've said that to get a 0 in row 2, you'll take row 2 minus 3 row 1. And to get a 0 in this position, we'll take row 3 minus row 1. So let's just do these operations. So this element times 3 subtracted from this, it was 0. This element times 3 gives you 3 out of 2. Subtracted from negative 3, this gives me negative 9 over 2. Because the LCM here will be 2. And this will be negative 6, then negative 3. So it's negative 9 over 2. So, okay. So we are done with this. Now this element here times 3, you get negative 3. And then subtracted from negative 1. Subtracted from negative 1. So this becomes positive. And that's why you have 2 here. Do that for the entire row, and you have this. You get this. Do it for the entire row, because I've also multiplied this by 3 to get 3 over 2, and then subtract it from 0. So I have negative 3 over 2. So I'm doing it the entire row. Now come to row 3. We've said we shall take row 3 minus row 1. So 1 minus 1 gives us 0. Negative 2 minus a half gives us negative 5 over 2. And then 3 minus 1 gives us 4. So you do it for the entire row, and you have this. Now, so the next thing is to create a 1 in this position. So how do you create a 1 in this position? By multiplying row 2 by negative 2 over 9. So multiply row 2 by negative 2 over 9. So you multiply the entire row by that, and that will give you 1 in that position. Because we want this 1, and then use it to create zeros in these other positions. So let's see what happened. Yes, so that's what I did. I just multiplied row 2 by negative 2 over 9. So when that happens, this by negative 2 over 9 gives me positive 1. This by 2, negative 2 over 9 gives me negative 4 over 9. And this one by negative 2 over 9 gives me a third. And this, the other one will give me negative 2 over 9. And the other one will give me 0. Now, once I have this one, I use it to create 0 in the other positions in column 2. So I want a 0 above it and a 0 below it. I want a 0 above. So I come here. How do I get a 0 here? So for me to get a 0 here, I require that I take row 1 minus a half of row 2. That's what I wrote. And for me to get a 0 here, I require that I take row 3 plus 5 out of 2 of row 2. And that's what I wrote here. So let's do those operations and see what they yield. So row 2 remains where it is, because it's the one we're using to create zeros in this position and this other position. So row 2 remains where it is. So a half of this subtracted from this a half gives me 0. A half of this subtracted from this negative 1 gives me negative 7 over 9. A half of 1 over 3 subtracted from a half gives me a third. And then a half of this subtracted from 0 gives me 1 over 9. A half of 0 subtracted from 0 gives me 0. We want a 0 here. They said we'll take 5 over 2 of this plus this. So 5 over 2 of 1 plus 5 plus this gives me 0. 5 over 2 of this plus this gives me 1. You can just work out that one, because this is 4 plus 5 over 2 of negative 4 over 9. And you see that 2 go here negative 2 times. So what we have will be 4 minus 10 over 9. And that the LCM is 9. And this will be 36 minus 10, which gives you 26 out of 9. Which one was that? It was, where are we? Yes, that 26 over 9 here. 26 over 9. So I think I was pointing at the same, at a different value. So this is 26 over 9. 26 over 9. So 5 over 2, we are done with this. 5 over 2 of this, then plus this, it gives us that. So you do it for the entire row, and this is what you get, this matrix. Get that matrix. Now, so the next thing, we have a 1 here, we have a 1 in this position, we require a 1 in this position. So how do we get a 1 in this position? By multiplying row 3 by 9 over 26. So row 3 by 9 over 26, the entire row 3 by 9 over 26. This will be 1. This will give us 3 over 26. This will give us negative 5 over 26. And this will give us 9 over 26. Now that we have this one, we want to use it to create a 0 in this position and another 0 in this position. So how do we get those zeros? And that's what I wrote in my next step. My next step, I said that to get a 0, in this position, I'll take row 2, the element in row 2, plus 4/9 of element in row 3. So the element in row 2 plus 4/9 of element in row 3. I do it for the entire row. And then for me to get a 0 in this position, I'll take the element in row 1 plus 7/9 of the element in row 3. And I do it for the entire row. And that's what I wrote here. So when you do that, you achieve this matrix. That's the matrix you achieve. Now you can see that we've achieved the identity matrix in this position, so that whatever is here is the inverse that we wanted to get. So that is the inverse. And that's what we have. So that's how we use Gauss-Jordan or row reduction method to find the inverse of matrices. Let's now, in the next video, focus on how to solve systems of linear equations by use of inverses. Thank you. Welcome to my channel, and this time we want to look at how to find solutions to a system of linear equations by using inverse matrix. So if you're given a system of linear equation, the first thing we'll be doing is extract the augmented matrix, then find the inverse of that matrix, and then use that inverse to find the solution to the system. So let's begin by the first example here. And the first example says, by finding the inverse of a matrix, solve the following system. So what I do, I extract the augmented matrix, and this is 1, 2, -4, -1, -1, 3, -1, -2, 5, and find the inverse of that matrix. So to find the inverse of this matrix, we have various methods, and we'll just employ one of the methods. So the one that I've used is the row reduction, but you may want to use the other method because we've already learned on how to find the inverse of matrices. Now by row reduction, you remember we said that for us to get the inverse of this matrix, we'll want to carry out elemental row operations on this. So I've just written the matrix here, then beside it I've written the identity matrix. So I want to carry out elemental row operations on this to transform this matrix to identity matrix. Once this becomes identity matrix, whatever shall be here will be the inverse of this matrix. And we've already gone through this process. We are all aware of it. So let's just do that. I have this one. I want the zeros here and here. So I'll take row 1 plus row 2. That will give me a 0 in this position. And row 1 plus row 3 would give me a 0 in this position. So let's do that. So 1 plus -1 is 0. 2 plus -1 is 1. -4 plus 3 will be -1. And to do that, 1 plus that will be 1, 0 plus that will be 1, and 0 plus that. So you have the entire row there. Then what about the row 3? This plus that will be 0, this plus that will be 0, and this plus that will be 1 positive. This plus that will be 1, this plus that will be 0, this plus that will be 1. So this is 1, 0, 1. Okay. So once we've done that, we've achieved the first thing, that we have 1 in this position and zeros elsewhere in the column. So we now come to this one, and we want it to be the only non-zero element in column 2. In other words, we need a 0 in this position and then a 0 in this other position. Luckily, we have a 0 here. So we only need to get a 0 in this position. How to get it? By taking row 1 minus 2 row 2. That's what I wrote here. So let's just see what happens. Maybe let's move this up. Just want to move it slightly. It's okay. Just let's move it slightly, that I have the two matrices to refer to. That's good. Now, so I want a 0 here. So it's row 1 minus 2 row 2. So in other words, 2 minus 2 multiplied by this gives me 0. Negative 4 minus 2 multiplied by this gives me negative 2. 1 minus 2 multiplied by this gives me negative 1. 0 minus 2 multiplied by 1 gives me negative 2. Then finally I have a 0. Now, so I've achieved that I have 1 here, elsewhere I have a 0. I have 1 here, elsewhere I have 0 in the column. So I now have this 1, and I want to use it to get zeros elsewhere in this column. So what do I do? For this row 2, I only need to take the row 2 element plus row 3 element. Row 2 element plus row 3 element. And for this position, I'll take row 1 element plus 2 row 3 elements. So when you do that, what do you get? This plus this gives me 0. Gives me that 0. This plus this gives me 2. This plus this gives me 1. This plus this gives me 1. What about this plus 2 times this? Gives me 0. This negative 1 plus 2 times this gives me 1. Negative 2 plus 2 times this gives me negative 2. And 0 plus 2 times 1 gives me 2. I've achieved what I wanted. I wanted the matrix that was here to become identity matrix. And I can see it has already become identity matrix. What means? That means that whatever was here, whatever is now here, is the inverse of the matrix that we were given. So I now have the inverse. And that's why I wrote and said that thus the inverse of this matrix is this. Just extracted like this one to become the inverse. Now that I have the inverse, I want to use it to get a solution to that system. So I multiply by the inverse on both sides. Remember that this is my inverse, and these were the augmented matrix I extracted from that system. Then multiply by the elements, the unknowns in the system. The unknowns in the system are A, B, C. This was A, B, C, A, B, C, A, B, C. So I put it in a vertical, in column form, A, B, C. It would give us the same result. It should give us this, that I should multiply the inverse on the left of whatever was, where did I get this 235 from? Let me show I got 235 from. I just go back to the system, and I see 235, 235. And ABC got them from here, ABC, 235. So let's see. Let's go back and just multiply. And we know how to multiply matrices. So when you multiply these, since these two are inverses of each other, they'll give us 1, 1, 0, 0, the identity matrix. Give us the identity matrix. And a matrix times its inverse gives us the identity matrix. So these two would give us this, then times ABC. And this product on the right side gives us 6, 12, 7. This product on the left side gives us ABC. And this remains as 6, 12, 5. So we found the result to the system. This is the solution to that system. That the value of A is 6, the value of B is 12, and the value of C is 7. I want us to take one more example so that our work will become familiar with this type of working. What is the question? The question, the next example is, find this inverse and use it to solve this system. Whenever this question is asked, you can see that the matrix here are the coefficients of this. So you can see that this is 2, 1, negative 2, 2, 1, negative 2. This is 3, negative 3, 1, negative 1. 3, negative 3, negative 1, and this is 1, negative 2, 3, 1, negative 2, 3. So whenever this question is asked, then you must know that this inverse just comes from this system. So we want to find the inverse of this. In our previous example, we looked at finding the inverse of this using row reduction. This time I want us to find this inverse by use of the adjoint method. So, and I said there are various methods. It's upon you to choose which method you want to use to find the inverse, unless if the question has specified for the method. Now, so using the adjoint method, and we saw this in our previous video where we're looking at how to find the inverse of matrix by adjoint method. So to find the inverse of the adjoint method, the first thing I did was to find the determinant of this matrix. And again, you have various ways of doing that. And let's look at this method, and you know this method. So to find the determinant of this matrix, multiply these entries, and then this as you add. Then multiply along this diagonal, along this diagonal, along this diagonal as you subtract, and you get negative 26 as your determinant. Once you've gotten negative 26 as your determinant, proceed to get the cofactor matrix. The cofactor matrix, just as we did in our previous video. And this is the cofactor matrix. Let me just, for those who have not watched the video, let me just show you what we did. But you must go and watch the video so that you are familiar with how to get the inverse of matrix by adjoint method. Now, so to get, this is the matrix you have. 2, 1, negative 2, 3, negative 3, and negative 1, 1, negative 2, and 3. And we want to get the cofactor, so we go for the cofactor in this position. Just delete this row and this column, and it will be the determinant of the matrix that is left when you delete that row and that column. So that's why you see in my working I have negative 3, negative 1, negative 2, and 3. Then we'll have minus. This time we are in this position, so delete this row and this column. So when you delete that row and that column, what do you get? Let me just reverse this a bit. So when you delete this row and this column, what is left is 3, -1, and 1, 3. The determinant of that. So that's what we are seeing in my working here. That's what we are seeing, and that's how I did it. You can see I have this determinant, then this determinant, then that determinant, and so on. You then find those determinants. When you find those determinants, this is the matrix you obtain. This is what you get. So the adjoint of this of the earlier matrix is the transpose of this matrix. So the transpose of this matrix is this, and we have already defined what the transpose of matrix is in our earlier video. It's just a matrix you get when you write the first row to be the first column, the second row to be the second column, the third row to be the third column. So this is the adjoint of A. So the inverse of A is 1 over determinant of A times the adjoint of A. And you had already found the determinant of A as -26. So that the inverse of A becomes this. Now once you have the inverse, multiply that inverse to the left of the coefficient matrix. I have multiplied to the left of this matrix. This matrix we get it from our system. Then times x, y, z, and this inverse multiplied by what our solution to the system was, the solutions to the equations. Because the first equation, it was equal to 6, and then the second equation was equal to 5, then the third equation equal to 3. So that is why you see 6, 5, 3. I got it from there. 6, 5, 3. And as I've already explained the previous example, these two give us identity matrix. And identity matrix times this xyz gives us xyz. And when you multiply the right hand side, this is what we got. So this becomes the solution to the system that we are given. And the method that will be used is the method of finding the inverse of the matrix. Thank you for being with me from the start of this lesson. We've now come to the end of this lesson, and I just remind you that if you've not subscribed, remember to subscribe so that whenever I upload other videos, you can automatically receive them. Thank you.